Welcome to the OscopeWizard. It is Tuesday. No special names for Tuesday because Tuesday seems pretty good on its own. And I am Gabe, the OscopeWizard. I'm glad that you have taken the time to join me this morning to hang out for a little while and nerd out. We just got through the weekend, and actually, it was kind of an eventful weekend because Baby Friday, during the last show, little OscopeWizard dude, my son, he was out having a Nerf battle with his friends. And while I was talking to you, he managed to fall off some stairs and fracture his arm. So we had some excitement over the weekend getting the arm fixed up and casted up. It actually didn't need a cast, which was good, because that meant we could still get wet. And it is the summer, and we spend a lot of time in pools and swimming when we can. But he is okay. He is okay. He's doing great. The only downside of having a broken arm in the summer is you can't really do Nerf battles with a broken arm because the doctor said it's only broken right now, but if you really snap that thing, it's a much bigger deal. So we're taking it easy, and in that vein, we've actually spent a little bit of time discussing video games. So he and I have a goal this summer. It might just be my goal, but we're trying to get to Gold League in StarCraft 2. I don't know if you've ever played StarCraft 2, but it's a very competitive online video game of real-time strategy. It's little armies trying to fight each other, and he and I have been playing together versus other teams of random duos on the internet, and we are trying to battle our way up the leagues. And so we are stuck in Silver League, which is beginner's league, and we're trying to get up to Gold League. It's something fun that we do, and we nerd out. I don't know, what video games are you playing this summer? Are you playing video games? Do you still play video games? I mean, I've talked about video games a lot on the show because I love them. I think they're a lot of fun, but I know different strokes for different folks. What else did we do? Oh, this morning, there was an oscilloscope emergency next door. My neighbor had a transformer for his outdoor lights, and he wanted to know what was the voltage on it. So I loaded up my oscilloscope very quickly. You can see it right here. And hooked it up to his wires of his outdoor transformer, and it turns out that the 12-volt AC transformer is outputting 12 volts. Although they say 12 volts AC, what they mean is 12 volts AC RMS. That was a little bit confusing because the actual AC was more like, I don't know, like 40 volts peak to peak, which is pretty wild. But 12 volts RMS, which was thumbs up, perfect. Everybody was happy. Worked like a champ. Also, if you have a question about outdoor lighting, I am not the right person to answer it, but I will say this on outdoor lighting, and it got me thinking. I have some outdoor lights in my yard, and I use a DC transformer. So it's 12 volts DC, meaning that the waveform doesn't go up and down. It's a flat line. And my neighbor was using 12 volts AC, so that the line was going up and down. The benefit of using AC is that you do not have voltage drop along a very long run. And guess what has really long runs of wire? Outdoor lights, because you're stringing these things all up and down your driveway and all up and down your walkway, so you have all this wire strung everywhere. If I was to offer some advice, I think that I made the wrong decision in getting a DC transformer, and I should have gotten an AC transformer. So this is current OscopeWizard talking to former OscopeWizard. You did this. You failed. You failed. But there's hope. We could change it. We could make it better in the future. Yeah, I don't know. It's always a challenge when you're trying to do something that you've never done before. You make mistakes. I've made a lot of mistakes on the show, and in fact, in the next show, I plan on trying a new camera. So I got a new camera in the mail to see if I could make just the picture a little better and work a little better. And also the camera that I'm using right now is not my camera. I'm kind of borrowing it / kind of stole it from a friend. They live in the neighborhood, they know where I live, and they'll probably come and get it eventually. So I have gotten this new camera, and we're going to try some more stuff on the show. What we've been trying on the show, let's get to the actual meat of the matter. And my 20-minute timer is outside. Let me set up a 20, I think I can actually set up a 20-minute timer on my phone. I believe I've used this in the past. There we go. We have a 20-minute timer set up on the phone. Right there, looking good. Keep us on track. Always need to be kept on track. What we had been doing on the show is looking at this tiny little amplifier board. And we have looked at it inside and out. We measured the power going to the amplifier. We measured the voltage drop when the amplifier turned on. We adjusted the potentiometers to make sure that I got the maximally unclipped output voltage onto my speakers. I used these really cool cement resistors. I'd never used power resistors before, and definitely never used cement power resistors, but they're 8-ohm resistors. They replaced my speaker because we were also measuring the performance of the amplifier using Bode plots, if you'll remember. So that is telling me what the frequency response of the amplifier is going to look like in the frequency band that my ear holes work, which is 20 hertz to 20 kilohertz. And these power resistors burned a lot of power, which was thumbs up great. They also didn't hurt my ear holes because they don't make any noise. So the speakers burn the power, but hurt my ear holes in the process. So I think we have explored the analog, I would call this the analog section of our design. This is the analog waveform that actually interacts with our human hearing to get the signal into this input, though, to this analog input, to then be spit out this analog output. I have to have another device. And I was using my phone as my sound device, but ultimately, unsurprisingly probably, I want to use a Raspberry Pi. So that's what we're going to do today. We are going to start the digital section of our design. I'm very excited because in college, I actually did digital design. I mean, that's sort of like the thing that I studied. So let's go through what we are going to look at today. We are going to look at, see if I can make my slideshow work. I think I can. I think I can. There we go. We're going to start with a Raspberry Pi Zero. A Raspberry Pi Zero is a really tiny little single board computer. We will spend a lot of time with it in this project as we set it up. The Raspberry Pi Zero has Wi-Fi and Bluetooth radios, which is thumbs up for our project because I want to be able to send the music wirelessly from my device, my phone, my tablet, my computer, whatever it is. I want to send it wirelessly over the network to the Raspberry Pi that's going to do the processing. And then the Raspberry Pi is going to send the sound over to my amplifier eventually. But there's a little bit of a trick. So one thing that this Raspberry Pi Zero does not have, it does not have an audio output. If we go to the next slide, you'll see I have an HDMI output, I have a USB output, I have a USB input for power, but no audio output, which makes it a little bit tough. So what do we do to get the audio from the Raspberry Pi Zero out to my audio amplifier? Because my audio amplifier wants the audio in analog format. So just like a sound wave that's small that it's going to make big. There is a trick. There is another piece to this puzzle. We are going to use a DAC. So a DAC is a digital to analog converter chip. I have made videos on it before. If you find me on LinkedIn, if you can find me on Instagram, you can actually look me up on Instagram at OscopeWizard. On Instagram, you can see all my old videos that I have done, and one of them was on a digital analog converter chip because that's something that I'm curious about. So let's switch over really quickly to look at the web here. So First of all, we start out with the Raspberry Pi Zero. That's the one we're using. A Raspberry Pi Zero, not expensive, something that you can't afford. It's 10 bucks. Has Wi-Fi and Bluetooth, and it uses hardly any power. I mean, there's not much on this board, as you can see. It's a little processor chip. I think this is actually the processor chip, and I'm not sure which one is the processor chip, actually. I think the OscopeWizard would know that. He's not a chip wizard, though. But it does not have an analog audio output. So, come over here to eBay and order weird stuff off of eBay. Mrs. OscopeWizard's always picking on me because I get a box in the mail almost every day with some kind of weird little gizmo device, cement resistor. I got this weird HDMI out card. I got all kinds of weird stuff coming in the mail, which has led to some weird things on eBay and Amazon with some sellers that has gotten kind of crazy. And she's like, that never happens to me. And I'm like, well, probably because you're not ordering super weird stuff like me. So this is a DAC chip that has a tiny little digital to analog converter chip on it. The Texas Instruments PCM5102A. The interface is I2S. So what happens is the Raspberry Pi has this thing called a GPIO port, and you can see my mouse is pointing at these pins on the Raspberry Pi, and some of those pins output I2S data, or they can be configured to output I2S data. And this DAC chip is an I2S interface, and it receives the digital traffic and converts it from digital traffic into analog traffic out of this 3.5 millimeter audio jack, which is like a very standard audio jack. If cell phones still had audio jacks, come on cell phones, seriously, 3.5 millimeters, it's tiny. Get your audio jacks back. Get your audio jacks together. But when devices did have audio jacks, they were 3.5 millimeters, almost without fail. So this board is going to take that digital data, convert it to the analog data, which will go to the audio amplifier, and the audio amplifier will amplify the analog data to go to the speakers, and that will be our whole system. So we'll start, Raspberry Pi receives the data, sends it to the I2S DAC board, sends it to the audio board, sends it to the speakers. Awesome, awesome. While we are here, let's take a look at the pinout. So here is a picture that I got on the internet. On the internet, so you can Google this. You could Google Raspberry Pi I2S. That's what I did. I Googled Raspberry Pi. Oh, in other words, the board creates magic. That's what chat says. I'm not sure which board creates magic. Probably all the boards kind of create magic. It does feel a little bit magical. And this is one of the pieces of digital design that I love. You can hook up a couple of wires and just make magical things happen, which I have loved it since childhood. I loved it through college. I still love it as an old dude now with gray hair, just trying to make it happen. So let's look at the GPIO header. So here's the GPIO header on the Raspberry Pi Zero. This GPIO header is shared throughout all the current Raspberry Pis, and it is a 40-pin header. There's a bunch of stuff happening on the header. You have a 3.3 volt pin, which we are actually going to use. So we're going to use this 3.3 volt pin to go to my I2S board and actually power it from the GPIO header. And then GPIO 18 is going to be my bit clock, which is one of the pins of I2S. GPIO 19 down here is going to be my left-right clock. So when you have audio, you usually have a left signal and you have a right signal to go to your left ear and your right ear, and that is called stereo. Two signals, left and right. And then GPIO 21 down here at the very bottom of the header is the actual digital data output. So I have a bit clock, left-right clock, and then the actual data coming out. I really dig this website. If you guys have not used this website and you are doing Raspberry Pi stuff, do yourself a favor and go to pinout.xyz, and it just has all kinds of different data or different explanations of exactly what is coming out of your GPIO header. We are doing PCM pulse code modulation, PCM audio. You'll notice a lot of times you have a PCM wave file when you encode audio, if you've ever encoded MP3s or anything. And this tells you that this is a digital representation of the sampled analog usually used for digital audio output, understood by a DAC for high quality sound. That sounds exactly like what we're looking for, and you can see it's just a prettier picture than what I had before, but it also is interactive. So I use this website a lot when I'm setting up my Raspberry Pi project. So pinout.xyz, thumbs up from the OscopeWizard, use it, it's very helpful. And the question was 2-channel audio. There was a question in chat. 2-channel audio comes out in a single data stream. That is so true. That is a good point. So there's only one data output for let's see. Here is the actual data sheet for the, I love data sheets. I feel like we're overlooking data sheets when we're trying to get deep into a project, and if you overlook a data sheet, it can be real trouble. But there is only one data pin right here, the I2S data line, and there's one bit clock. And since there's only one data line, I need the digital audio converter chip to know, is this data for the left side or the right side? And that's where the left-right clock comes in. So it is modulating the left-right signal on a single data line. So a little bit of a time division. So time division multiplexing is happening with I2S. Thank you, chat, for pointing that out. I really appreciate it. You guys are great for keeping me straight. Let's go back to some pictures of what is actually on my board right now. So I had the Raspberry Pi and the DAC beside each other. The DAC does have the 3.5 mil connector, which is great. Now I have a whole mess of wires because one of the things I'm going to have to do is wire everything up. So this DAC chip has a ton of ins and outs, and I need to make sure that they're all kind of handled. So around the chip, I have a bunch of pins that are kind of outlined here in the data sheet, and I have a bunch of inputs. So 1, 2, 3, 4, 5, 6, 7, 8. 8 to do something with, because I can't let inputs float around, because if you let inputs float around with no connection, they are very unpredictable. It's very important that you connect your inputs, either high or low or whatever is prescribed in the data sheet. So a couple of them are super easy. The bit clock, easy. That's going straight from the GPIO pin of the Raspberry Pi into the DAC chip. The data input, easy. That's it. Easy. That is from pin 40 on the GPIO into the DAC chip. And then I think I have left-right clock right here. Yep. That is from GPIO 19 into the DAC chip, if I can get it out. And then mute. So mute was a little bit tough. So soft mute is holding the pin low. I don't want the chip to be muted, so I held pin 17 high. So I tied that up to 3.3 volts because this is a 3.3 volt part. So high is anything above 1.68 or 65 volts. This one, system clock, that actually can be left unplugged because when it is unplugged, it uses an internal clock per the data sheet. So I have left this unplugged. You see there's a little note right there. This is fail-safe. There's a trigger input. So if I want to support or bypass the internal PLL, phase lock loop of this chip, then I can send a signal into this S clock. I don't want to do that. I'm just using the chip's internal phase lock loop, which is its internal clock. The audio format, I have held low for I2S audio because I'm using I2S. The filter selection I have held low for normal latency. I'm not really sure what that might do. And then the de-emphasis control I have turned off. I don't want to deal with any de-emphasis or pre-emphasis or any emphasis beyond just the sound. There's a question, do you need any pull-up or pull-down resistors? I suspect that I may use pull-up or pull-down resistors. I don't even know if it is it specified in the datasheet. We have the digital input voltage. Anything specified in the datasheet? These are hard questions. Input logic level, VN, it doesn't, okay, so it doesn't want any more than 10 microamps. So you could run it through a kilo ohm resistor and, is that right, milliamps? No, you could do like a 10 kilo ohm resistor and you would be fine without, to avoid damaging your circuit. Now, I don't know if the GPIO pins of the Raspberry Pi output much current. The 3.3 volt supply line does output some current, but the logic lines, let's see. Raspberry Pi GPIO current limit. Let's see if there's anything. Okay. The operating voltage of the GPIO pins has a maximum current draw of 16 milliamps. I wonder if there's internal resistors. You guys are making good points. I should probably add some resistors to the final design. That is not in place today. That's not in place today. You can see what's in place today. In place today is this. So I have a bunch of wires. So here is all the pins on the DAC chip. Here's all the GPIO pins on the Raspberry Pi. Those two things are wired together with these jumper wires, and I have, here's the power connection, and then a whole bunch of digital connections to get this thing working. So it is a very good point in the chat. I should add some pull-up and pull-down resistors. And honestly, most of these are wired to ground because I held them low, and only one is wired high. So that is the only one that I would be worried would ever get current. So the one chip that is wired high is my soft mute. And because I wanted it unmuted, because I want the circuit active, and when it is low, it will not output sound. So everything else that I mentioned was wired low. So what I will ultimately do is solder all those to ground, probably with no resistor, because I wouldn't be worried about current flowing from ground up. There would be all kinds of disasters there. But the soft mute is going to be wired to a GPIO pin from the Raspberry Pi. I may put 16 milliamps, so I'd need to drop that down to microamps, which is 1,000 times less than a milli. So I see it in there, a kilo ohm resistor between the GPIO pin and the soft mute control, just to make sure that I limit the current to the 10 microamps prescribed by this datasheet. So I think there will be a 1 kilo ohm resistor between the GPIO pin and this soft mute control, because I want the Raspberry Pi to control the soft mute of the DAC chip. That's a good point. It's a good point, folks. Thank you so much in the chat for keeping me straight. So if I go back over here, I talked through that. I was actually looking at the datasheet. Sorry, guys. I was looking at the datasheet. Y'all didn't have it. Sorry. If I turn on my webcam, you can see this is the live shot of my setup. if I go over here, I've actually hooked up a couple extra things. So besides having all the digital lines hooked up, right here I have an oscilloscope probe, an analog oscilloscope probe, hooked up to my audio output channel, one half of my audio output channel. And then on the back here, I have some, let's see if I can pick this up a little bit. I have my MSO line. So I haven't talked about MSO. Oh my gosh. Oh my gosh.
5 minutes remaining!
5 minutes left, guys. Let's talk about the MSO really quickly. We have everything plugged in. So on Baby Friday, the next episode, we'll turn some stuff on and probably make sound happen with this DAC chip. But going back to my setup here, I have an MSO line. So an MSO line is a really cool tool. An MSO stands for Mixed Signal Oscilloscope. What this allows me to do is look at digital traffic with an oscilloscope as if it was a logic analyzer. Logic analyzers are old boxes that have died. They have sort of gone the way of the dinosaur. But people still have digital buses, you know. They still want to look at digital traffic, but they don't necessarily want to look at, you know, 600 lines of digital traffic. In my case, I'm looking at an I2S bus, which is 3 lines of digital traffic. I have a clock, I have a left-right clock, and I have data. That's it. So why would I hook up 1,000 lines? 3 lines is perfect. MSOs usually offer 16 channels of digital inputs. So your oscilloscope has its analog inputs, which is the channels that we have been using with my amplifier. It's the beautiful signals that you see waving around. We can see channel 1 on my oscilloscope right now is an analog input. But I have digital inputs as well that I can turn on. So I can go in here and enable a couple of buses or a couple of signals right here. And these will look like 1's and 0's. They will not have analog waveforms. They would just simply have 1's and 0's on them. And that is how digital traffic is communicated via 1 and 0. The advantage of using the MSO over the analog line to look at digital traffic is the MSO or digital lines require less data because I'm only looking at 2 states, either on or off, which is basically how digital boils down to 2 states, on or off. Everything in the world is governed by on or off. You can have multiple digital lines if you wanted in a bus, and then you could be 1, 2, or 3, or 4 on or offs all lined together, and that's how you can count up digitally. I don't know if we haven't ever covered the binary counting system, but that is a pretty big tenet of digital traffic. I don't know if maybe we'll do that a little bit. At the very least, on the next episode, we will definitely hook everything up, power it on, talk about digital traffic from the Raspberry Pi Zero over to the DAC chip. We'll also start exploring my different options for operating system because a Raspberry Pi Zero is a computer, a tiny little bitty computer that has a lot of powerful tools at its disposal, but some of those tools are only available in one operating system or another operating system. There's a lot of flavors of operating systems, so I'll talk a little bit about the 3 operating systems that I looked at before I chose the one that I'm going to use for my project. Although I'm going to leave it open, you know, if you have a great audio-based Raspberry Pi operating system or distribution or image, please let me know in the comments or on Twitter or Instagram at OscopeWizard. And eventually, another thing that I need to start looking into is what sort of box am I going to put this in? I don't know what it's going to look like. I'm not really great at making boxes. So if you have a friend or a desire or a love of boxes, point me in the right direction. Maybe there's a great design out there or a prefabricated box that I could manipulate a little bit to put my design into. Until next time, I don't know all the nerds in the world, but I'd love to meet them, so please share this with a nerd in your life. And I'm going to hang out in the chat a little bit. The chat has been great today, by the way, guys. You have helped me a ton, keeping me on track, asking great questions, pull up, pull down resistors, great questions. I'm going to explore that a little bit more. And I guess I will see you guys next time. Later.